Good afternoon, everyone, and welcome. Thank you for joining us. We are proud to present our next speaker, Diego Oppenheimer, with Algorithmia. Please give him a warm welcome.
Hey everyone, thank you for coming here today. Everybody can hear me all right? Great. So I'll be talking a little bit about continuous deployment for machine learning, but just before we start, just kind of quick show of hands. How many data scientists in the crowd? Great. DevOps engineers, cloud engineers, right? Machine learning engineers, everything else. Awesome, great. So I'm going to talk a little bit about kind of like why continuous deployment and kind of this new life cycle is emerging outside of machine learning. So I'm going to start with very quickly kind of talking about some of the problems that you're going to face and why they exist, and kind of they're certainly different in the world of machine learning than they are in the normal software development life cycle. And then just show a quick demo of what a pipeline could look like when you want trying to automate this all at once. So to start with, we went out, surveyed about 600 people last summer in the world of enterprise machine learning. What we realized was about 75% of the time the data scientists and machine learning engineers were actually spending on infrastructure-related tasks that had nothing to do with actually building the models. And so when you're deep diving a little bit more into what they look like, things that they were dealing with were things like supporting different languages and frameworks, actually going into supporting different model management, so how you actually do versioning, what versions are actually going into production versus which ones are not, and then deploying which ones at scale. And every single one of these is not only a pain for the actual machine learning engineers and data scientists, but actually is also a huge pain for all the DevOps engineers, cloud engineers, IT engineers that actually have to go deal with it. And so this is a compounding problem, and I'll talk a little bit deeper about how that looks like. So what are the things that are happening that are different in the world of machine learning, data science that we might have not seen traditionally? So the first thing is that there are dozens of languages and different frameworks and combinations thereof that are actually being used. We're seeing different hardware dependencies, so CPUs, GPUs, different drivers that are needed for each one of those. And when you're giving, actually in any one of these frameworks, you're actually giving multiple versions and different versions of that actually might behave slightly different in a very quickly evolving pace of what we're seeing across the industry. And so to solve many of these challenges, the intent of companies and organizations is actually to freeze those training and production environments through containerization and say, hey, we're going to capture the entire environment, try to get a static, and then deploy that and keep on using it. The problem is as these models keep on evolving, the dependencies also evolve, the frameworks also evolve, and that intent of freezing actually kind of like falls through, and that doesn't really work well. So we're also seeing that a number of these different frameworks are actually contain their own deployment tools. So you could be in a situation where inside your organization you're running TensorFlow and trying to deploy that on TensorRT, you're running PyTorch, you're trying to deploy that with its own deployment tool, and MXNet, and each one of these actually adds its own complexity. So the second challenge that comes out when you're actually working in machine learning is composability. So machine learning models rarely actually live in isolation. So you have actually pipelines, one model that goes into the next and goes into the next, and how actually these can actually be componentized. So in this particular example, I have a PR firm that's actually scanning documents, doing OCR on a couple of documents using R and a certain version of a text OCR model, putting that through a language identifier, which might be in scikit-learn, which might be in Python, which might be GPU accelerated. If it's English, it's going into a text vectorizer that might be written in Java. If it's not, going into a translator, and then going to sentiment analysis. The reason why I'm showing this is that this type of complexity around model pipelining is fairly common. So now we look at this and we have 1, 2, 3, 4 different languages and frameworks being used, each one of them with their own dependency management, each one of them potentially with their own hardware management, and each one with its own unique environment. So this is the actual complexity of actually going into production that now needs to be managed in a way where at any given time, each one of these components needs to be able to be updated with the new versions. And so this is kind of where we're talking about it is necessary to kind of start thinking about like, okay, well, how do I do this in an automated fashion? Because manually doing this work is really going to become impossible dealing with those frameworks. So the other big difference is that the difference between normal software development and actual machine is that there's actually two distinct stages in the world of machine learning that have really different characteristics. So the first one is training. So when we look at that, what we're usually is very large data sets. We're running the models, we're training them, we're iterating multiple times over them, we're experimenting, we're changing the hyperparameters. Usually they are very long, intense compute cycles. They have fixed inelastic loads, usually a single user, and then sometimes you run concurrent experiments on a single model. Once you have selected the right model, or you're actually ready to use that model, you're going to move it into production, you have a much different architecture, which is really around inference and how you actually do that, which changes its characteristics. It's much more about short, unpredictable compute bursts. So I might have a model that goes live. It's being called by 100,000 cell phones at 2 o'clock and only 10,000 cell phones at 3. It's highly, it has to have high scalability, high concurrency, and it's many users will be consuming that at the same time. So in both of these, you have a different style of operation that actually needs to be maintained, but you have to have a constant cycle of how these models are actually getting trained and then pushed into production through a continuous deployment lifecycle. So the next component that's really important is that in the normal software development lifecycle, you go through build, test, deploy, and monitor. And that is something that happens pretty commonly, but that might happen once a sprint, maybe a couple times a week. If you have a really fast-moving application, a couple times a day. In the world of machine learning, this iteration might be multiple times an hour, right? So as new data is coming in, we're putting through new training. We're actually retraining the model sometimes in real time. We're pushing a new version into it, and that's actually being called. And that actually pretty much makes it impossible for human intervention. We really have to automate all of this so that deployment is constant, testing is constant, and we can actually go through that. And so the combination of the ecosystem really evolving, the ML actually build out being a lot moving faster, and the fact that each one of these can actually introduce breaking changes becomes important. So you can see how your applications are going to be calling these models, and it's important to be able to catch, roll back in the same way that you do this with any other type of application. So the last aspect of it is that this diversity also complicates the way you actually do logging, monitoring, compliance, and governance. So while in a common stack, you can actually see, hey, this is how we're going to actually look at all the changes that we made over the life of the application. Now you actually might have multiple different versions of models, multiple different frameworks that are being called, and how you're actually doing that governance and manageability becomes more complex. So you have to have a model in which you can actually put all of these models under one roof and understand how they're being called, how they're being governed, and how you audit them in a good way, in a proper way. So as a result of machine learning being faster and more frequent, the traditional app development workflow, this is really what we need to start thinking about, how we do versioning and how we actually do that governance in a more standardized way. So the solution is to start thinking about continuous deployment for machine learning. And so I'll walk through this fairly quickly, in detail. So programmatically, you want to be able to connect to your data. So you're going to have your data management systems. So think of this as your ETL systems, your pipelines, your data lakes, how you're actually grabbing all your data and they're being controlled. Those are going to be fed into your training platforms or frameworks. Inside a large organization, you'll probably have more than one data science team using more than one platform to be able to train and pull from that data. And you want to give them an automated way of actually pushing that into your production system, which should be taking care of deployment, serving, and management in one consistent way. So any of these frameworks need to be able to actually build out from that. They need to be able to be deployed into that, served, and then governed and audited all in the same way. So managing all those models and integrating them in a constant way is extremely important. And so what you want to do is that cycle, and I don't have a pointer, so I apologize. What you want to see is what I previously had shown in terms of that iteration cycle, is you want to see happening between your app, when your app is consuming, you want to see between your data management system, the data flowing down to your training platforms, your deployment serving management for serving it to the application, and as new data is coming in, something triggering so you have that process repeating itself. So very quickly, I'll jump through a demo here to kind of show you what that might look like, directly using the tools that software developers use today, like Git. So in this example, I'm going to use, obviously, what our company does is Algorithmia. We're actually on top of GitHub. using GitHub as the actual source of truth for the models and the code for it, and how you can actually use GitHub Actions to actually continuously deploy models into production in an automated way. So the first thing I'm going to go do ahead is actually produce a Git push. So what I have is, you're going to see here that I've actually trained a model. So you see up there a digits classifier, so the most basic of machine learning models, using scikit-learn, create my pickle file. I'm going to go ahead and Git push that. I Git push that into my master. It's actually going to say, okay, now you've updated your model deployment template. You're ready to go in the same way you've done that with any normal code or anybody who's done a Git push. We've configured a GitHub action to actually trigger off of every push into that master file to start actually doing a model deployment. And so I apologize for the visual here, but if you look down there, it's showing that it's actually going to go create a digit recognizer. It's going to create a bunch of details that are being pushed in as part of the metadata. So what is this model doing, what the summary is, what the tagline for it is, and the updates into it. It's going to go ahead and deploy that model automatically using GitHub itself and apply it inside Algorithmia in this case, where it's actually now created a landing page for that model or updated a new version. In this case, a digit recognizer. Documentation was already pushed through it in the metadata file that was already included inside GitHub. And it's actually going ahead and created an example. I'll be able to actually go hit run, which will actually run the example, in this case, that image, which is classifying it, and then be able to actually go ahead and produce the result, which should be a recognition of 1. So I slowed this all down in slides because it's very fast when it actually happens live. So I'll actually go ahead and now show the video of actually this going all ahead live and doing that. And so you can see the actual deployment. So what I was talking about, this iteration happening every second or every couple of minutes, this should be completely automatic. So now I actually have the ability of actually updating models without actually going, all the dependencies being pulled and the jobs actually gone and been created, and being able to actually see how in this case, my digit recognition model has actually gone live and done that. And so although there's a UI, this entire thing could have been programmatic. And what this really is start thinking about is, like, as we actually do machine learning, we really have to start thinking about where do we actually start, how we're going to actually end in production. Too many data science and machine learning projects only have the actual science part in mind. They never actually leave the R&D lab because we have to think about how are the applications that we run going to consume these. And when those applications are line of business applications, the value is about really having those models update while not affecting the production of those line of business applications. And so starting to think about the continuous deployment of those becomes extremely important. So with that said, thank you very much for your time. We have a booth all the way over there where we can give more in-depth demos, and we're happy to chat more. And I'm happy to actually have left a couple of minutes to answer any questions you might have. Yeah, so let me see if I'll repeat the question. So you said you have multiple different models, and they kind of pipeline into each other, which is what I was, yeah, exactly. So the idea here is that as you start separating them into the service-oriented architecture, you start considering them as kind of modular in the same way that you would build modular software. What you want is you want each one of them to not be dependent on each other, to actually take updates. So your models might be using different frameworks. They might have different dependencies. So you want that dependency management to be kind of like modularized to those models, and then you pipeline them together and deploy those pipelines all together. So the way that you would set up your CI/CD would be like, okay, now I can update each one of the components independently, but really what's happening is the entire pipeline is actually being updated together. Yeah, of course.
How do you handle models that exceed the GitHub limitation?
Sure. So the model, like the model size themselves, so what you put in GitHub is we actually put the code. You can actually put the models in any sort of blob storage or versioning storage and call them. So what you're really putting in GitHub is really the query code or the kind of the inference code that you're actually applying to the model. So the model file could be in S3, it could be in your on-premise blob storage, doesn't really matter. You can use some other versioning to actually pull it. But what you want to do is have that consistency, especially if you're working in regulated industries, which is some of the stuff that we actually work with. You want to be able to provide every single inference for every single version of the model you've created in case regulators ask you for that. And so that's something that you can package all together. And it's actually really easy to do when using something like Git on the back end. Big thing is, like, when you don't have to reinvent the wheel, don't. So there's a lot of really good concepts from basic software development lifecycle that are not being applied, like the use of Git, and version control and APIs, open API specs that are not really been applied to data science and machine learning. But once you do, they can really accelerate the time to production for machine learning models. Sorry? Yeah, so the output in this case will actually just be an API endpoint. So we produce 14 SDKs automatically, and we can show you at the booth. So we'll produce 14 SDKs completely automatically, but it's just an API endpoint. That API endpoint can be inside your VPC. It can be kind of anywhere you want, but what you really want to do is start thinking. The problem with monolithic applications is when you're trying to embed the machine learning model into the software application, you're almost for sure going to have like a difference between the lifecycle update of the application and the machine learning model. And so if you're actually gated by the by the team that's updating the application and say, hey, you can't update the model until we update the application, you're definitely going to have a problem with that machine learning model being completely out of date, or in the worst case, producing wrong results because the data has already shifted from it. Any other questions? Thank you very much for your time today, and feel free to stop by the booth. Happy to give you a more in-depth demo there. Appreciate it.